use as small windows that scan across the image. Output 55 multiply. The image shrink, but we get 48 different features, maps. Each filter dedicates a different features as texture, etc. Now actions to rectify the linear unit. This simply makes sure all degree values become zero. Faster learning. Without these deep networks suffer from something called the vanishing gradient problem. Vanishing gradient problem. What does that mean? Okay, I use this one like instead of just keep switching from place to another, you can just vanishing. So the vanishing gradient problem is a significant challenge in training deep neural network, especially those with many layers. It occurs when the gradient of the loss function with respect to the model parameters become exceedingly small as they are propagated backward through the network during training. This can lead to the following issue. Slow learning. If the gradients are very small, if the gradients are very small, the model weights are updated very little, effectively preventing the model from learning. This is particularly problematic in deeper network because the gradient can diminish and it's moved backward through layers. Stuck training. In some cases, certain layers may stop learning entirely because the gradient is too small to cause any meaningful change the weight, resulting in a model that doesn't improve. The causes the vanishing gradient problem is often associated with a certain activation function, such as the sigmoid or the tan function, which can be squash their input into a small range. As the gradient are the back propagated, they can shrink significantly when passing through these functions, especially in deep network solution. Several techniques have been developed to mitigate this vanishing gradient problem. Activation function. Using activation function like rectified linear units, variant patch normalization. So cool. So max pooling layer. Shrink the features maps to reduce competition and focus on the most important features. Think of these as looking at an image and only keeping the most important details. Deeper convolutional layer and more pooling. Stacking multiple convolutional layers helps detect more complex patterns. Lower layers detects edge, with the higher layers detects full object like cat's face. Fully connected layers. After enough convolutional and pooling, the features are flattened into a vector and passed into traditional neural network for final classification. Key insight: instead of manually choosing features, AlexNet learn features by itself from data. It uses two GPU graphic processors to handle the large computation. Scaling up VGG 2014 after AlexNet researchers asked what's if we go deeper. This led to the VGG 16 CNN with the 16 layers, which was an improvement over AlexNet. Key differences from AlexNet: use 3 multiply 3 filter instead of large 11 times 11 ones. Use more layers, deeper network can learn complex patterns. Still follow the same basic structure, convolutional is pulling fully connected layers. PGG main lesson. This one. Why does depth matter? Think of the CN as hierarchy. First layers detect edge, middle layer patterns, and last layer recognize object. Deeper network allow finer details to be captured. However, they come with the challenges. More computations take longer to train. Vanishing gradient, early layers stop learning in very deep networks. PGG. Fully connected layers, VS convolutional. Fully connected layers like traditional network trees, all pixels equal, which isn't efficient for image. CNN skips this. The spatial structure by using convolutional adenosine. What is come next after VGG research built even deeper networks? This net 2012 solved the problem of vanishing gradient by using skip connection. Inception GoogleNet 2000 used multiple filter sites at the same time to capture features at different scale. Efficient net optimized CNN to be smaller and faster without losing accuracy. Summary: CNNs revolutionize image recognition by automating features extraction. AlexNet 2021 ImageNet by stacking convolutional layers and using new VGG16 went deeper with the small 3 multiplied by 3 filters, more depth, capture better features, but it also bring challenges. Modern network use even deeper architectures like one efficient this one, blah blah blah. Okay, so um, mostly like I document the things really learn. Like for instance, just like I'll show to you what I mean by that. Come on. So I'm now here, 422. I think this is 443 now. I'm gonna add page. So I mostly like document everything for each book, which is here's the chapters. Okay, and as well I'm gonna add this one, the vanishing gradient problem. We might in the future need to read somehow about these things. No, control Z back. You see like here the gradient descent. If I learned something about the gradient descent, it just be documented. Logistic regression. Not okay. Add code. Here's the code. probabilities, data handling, multi-layers perceptron, and for this one, make it subpage and make subpage and yeah. So convolutional neural networks have become a driving techniques behind a lot of progresses in computer vision. It is therefore okay. I'm gonna pray and I will be back. I will pause. My favorite drink, it's called mate. So, back to the track. So, convolutional neural networks have become a driving techniques behind a lot of progress in computer vision. It is therefore useful to dig a bit deeper into this. Discuss how CNN are implementing researchers ask, what if we make networks even deeper? They tried stacking more layers, expecting high accuracy, but they hit a problem. The
Cross mark the degradation problem.
the degradation problem. Okay. As the network got deeper, example 30 layers, the, they stopped improving. Surprisingly, deep networks perform worse than a slower network. When increasing the number of layers in a model leads to worse performance, even when the model is probably trained. This issue can seem having more key point of the degradation problem. Mm, As more layer added, the training error may continue to decrease. As more layer added, the training error may continue to decrease, but the validation error might start to increase, indicating overfitting or that the model is becoming less effective at generalizing, vanishing, exploring, deep. Even with the proper initialization optimization challenge as become deeper. It's become increasingly Okay, so the residual network, it is introduced by Kimming here. Network use skip connection or shortcut. They allow gradient to flow through the network without diminishing, mitigating some issue caused by the diff. Patch normalization. This technique helps maintain the distribution of input to each layer, which can stabilize training and improve convergence in deeper networks. Skip connection, similar to ResNets, adding skip connection as other architectures can help avoid degradation by allowing gradient to bypass layers and improve learning dynamics. Better initialization using advanced weight initialization strategies can help ensure that the deeper layers start from better position in the loss landscape, better dynamic layer scaling, and so gradient vanishing or exploding. It's called culprit.
Culprit.
Very deep network gradients shrink or explode as they propagated. stop learning because the update become too small. This makes it impossible to train deep networks effectively. So ResNet solved this with skip connection, the residual learning. The key innovation, residual learning. Instead of learning a direct mapping from input X to output Y, ResNet learns residual function y equal fx plus x. What does this mean? Instead of computing y equal fx directly, the network learns the difference between y and x. Example, if fx equal y minus x, then it add x back after fx is computed. Skip connection shortcut path. Each ResNet block includes a skip connection. The input X is copied and added back to the output after new layers. This allows gradient to follow directly through the shortcut, preventing vanishing gradient. Imagine climbing a mountain with the backpack. Without ResNet, you must carry everything yourself. Each layer computes from scratch. With ResNet, you can store, import items and checkpoints. Skip connection make the climb easier. ResNet architectures 18 layers, 34, 50, 101, and 152. ResNet and above use bottleneck blocks instead of basic blocks to improve efficiency. Basic residual block used in ResNet 18s and ResNet 34. A simple network block like this one, where fx is a small set of convolution. Batch norm, what does that mean? Okay. Real operation structure 3 convolutional conv batch net skip connection x is added RLU if x this one where fx is small set of convolutional benchmark this one structure 3 multiplied by 3 convex release skip connection if x and fx have the same dimension we can add them directly. Bottleneck residual block used in beyond to improve deeper one-to-one convolutional reduce channel, 3 to 3 convolutional extract feature, 1 to 1 expand channels back, skip channels plus. Why does ResNet work? Avoid vanishing gradient. Skip connection allow gradient to through the network, easier to optimize each layer only needs small
I want you to imagine approximating a function parameterized by a deep neural network. In this example, we're going to pass our network an upsampled low-resolution input image and pass it through each of the network layers. We want the network to output the input image, but now in a high resolution, a task commonly known as super resolution. Unfortunately, in practice, after training our network on high and low resolution image pairs, somehow our network is spitting out images that are even worse than our input. After putting all your effort into a beautifully deep architecture, you are horrified to see that instead of going down, your training loss shoots endlessly upwards. Your classmates and colleagues can't help but laugh. And seemingly counterintuitive because now the model has more parameters. Now, how can we address this and get your loss going in the right direction? This problem partly comes down to the fact that we have an input signal that is being lost the deeper and deeper we go into our network, as the signal is passed through each of the nonlinear functions at each layer. Look at what can happen to a training signal even after
When I moved to Luxembourg, EIB helped me a lot with the allowance and the best neighborhood to live.
Welcome back. So today we're talking about the residual network, or ResNet architecture, which is one of the most important modern deep recurrent neural network architectures used in all kinds of applications, from super resolution to image classification to modeling physical. Welcome back. So today we're talking about the residual network, or ResNet architecture, which is one of the most important modern deep recurrent neural network architectures used in all kinds of applications, from super resolution to image classification to modeling physical systems like ordinary differential equations. Okay, good. So let's jump right into it. So generally speaking, we might want to be modeling some input-output function using a neural network. So our inputs x and our outputs y. The relationship between these could be some function f that we're trying to approximate with a neural network. And I really like motivating ResNets with a super resolution example because I think this makes the most intuitive sense to me, where maybe X is a low-res image of something like this fluid flow. And my goal with this neural network is to get an output Y that is a high resolution, a super resolution version of that image. Now, there's lots of ways of doing this, but the idea, kind of the intuitive idea behind ResNet, or residual network, is instead of trying to learn this mapping from X to Y, why don't I take and create a copy of X and only try to model the difference between X and the desired output Y? Because in this super resolution task, most of the information in the output Y actually does already exist in this low resolution input X. And there is a relatively small residual F that captures all of the little features that I'm trying to model here. So we'll get into why this is a good idea later, and this is a good idea for lots and lots and lots of reasons. If I want to make an increasingly deep neural network, oftentimes it is hard to remember the input X over many, many, many layers. There's this kind of notion of forgetting in neural networks. Over many, many layers, it's easy to forget the original input X. And in lots of cases, the output is actually pretty close to X, so we don't want to forget that input. And so residual networks are a really, really powerful idea introduced in 2015 that essentially allows us to train much, much deeper networks without forgetting the input at the final stages of the network. And essentially, this idea of modeling only the residual, so you create a copy of the input and you add to it some residual f that captures all of the little kind of delta changes from input to output. It's a really clever idea, and it also makes a lot of sense if you think about, like if you're like me and your background is in applied math and computational science, this makes a lot of sense that oftentimes we would only want to spend our effort modeling the residual, the thing that we don't know between x and y. So really, really cool architecture and easily motivated by this super resolution example. We're only going to model the small differences between these two figures that we need to. Okay, good. So this is going to be the kind of schematic of what we're trying to do. We're trying to go from inputs to outputs, and we're going to essentially create this identity copy of our input, and we're going to add to it all of the stuff that our neural network thinks is important to get to this output y. And this is kind of the standard generic set of items that go into a ResNet block. In principle, this is pretty customizable. You don't have to use this cookie cutter ResNet block. You could do other things. You could use other activation functions, other kinds of normalization and convolutional networks. But the basic idea, if you're going to build a ResNet, is to have these kind of pieces here where you might have some kind of a convolutional layer, some normalization, some activation function, another conv layer, another normalization. And then once you add this x back to itself, you'll then go through a final ReLU activation in the kind of standard ResNet block. Now you'll notice that if I have these convolutional layers with stride 1 and padding of 1, kind of the input dimension in the input side of this and the output dimensions on the output side of this are the same size. So that's really good if I want to process, where x and y are kind of the same size objects. Now, this might be a little confusing in the example I gave earlier because this is a low resolution version of this. But what you would do is you would take this low res image and you would basically just create a version of it that is as high of a resolution as your desired output Y, where each of these little blocks is just repeated pixel values over those high resolution pixel blocks. So you can basically create a high resolution image from this low resolution image where each of these little square blocks might have like 9 pixels of the exact same value inside of them. And so now this kind of low resolution image still has the same number of pixels as this desired high resolution output image. So X and Y are the same kind of size, if you like. So that is the kind of idea here of using Stride 1 and Pad 1 is that you can have your inputs and outputs be the same size, so the same size image. And again, just the motivation behind this, I think at least one of the main motivations was we knew after 2012, after kind of the big success on ImageNet, that the deeper the neural network, typically the better performance you could get on these really hard tasks in image classification. Typically, the better ImageNet, that the deeper the neural network, typically the better performance you could get on these really hard tasks in image classification and natural language processing. And so the push after 2012 was to make deeper and deeper and deeper networks. But oftentimes you had these really, really nasty problems of forgetting your input signal, and it was hard to train these deep neural networks because backpropagation would get a little bit ill-conditioned and finicky. And so this ResNet block here that essentially bypasses some of those issues by having this jump connection, or skip connection as it's called, where you create a copy of the input and just kind of manually add it forward after the neural network models the residual. That allows you to train these much, much deeper neural networks without forgetting and typically having a better backpropagation of loss errors. And so this is kind of a schematic of the ResNet architecture used in this CVPR 2015 paper, and you can see that it's super, super deep, right? 34-layer plane, 34-layer residual, really, really deep network, deeper than other networks at the time had been able to achieve and train reliably. So that's one of the huge benefits of these ResNets, is that you can go deeper, which we know gives us more expressive capability for really, really hard problems, if we have enough training data and enough computational resources. A couple points I want to make. I showed you this ResNet block where you have these kind of convolutional layers that are designed to keep X and Y as the same size. So if I want to go from image to image, this is a good ResNet block. You can also use these for classification tasks, where you want to go from something big like an image down to a small set of distilled kind of features for classification. The way you might do that is you could, for example, have your stride equal 2 here, so you're actually skipping over some pieces, but then have twice as many conv layers in here. So you can essentially, decrease the spatial dimension by a factor of 2, but increase the number of convolutional features also by a number of 2. And that's typically what's done when you want to use ResNets for a classification task, is you would take your high-res image and you would change your stride to 2 and have twice as many convolutional filters, and you might do that over and over again, and it would sequentially crunch this down into a smaller set of distilled features, just like a normal kind of convolutional neural net would do. You can do the same thing here. But I like thinking about kind of image
The key innovation, the inception model, instead of using the one GoogleNet multiple filter sets, simultaneously insertion, multi-scales, feature extraction. Imagine you are looking at the image, small details like texture are best captured by small features. The a 3 by 3 bigger structure like object are best captured by larger filters 5 by 5. Some information is best perceived by not filtering at all using pooling. How the inception model work. Organization instead of okay the key is alright small details. Yes, one convolutional feature reduction. Convolutional medium-scale features, convolutional large-scale features, max pooling, capture overall information. Max pooling, capture overall information. Output. GoogleNet architecturing. GoogleNet 22 layers, deep, layers deep, much deeper than AlexNet 8 layers, but it is computationally efficient because it uses inception models to reduce redundant parameters. It replaces large fully connected layers with the global average pooling. Convolutional multiplied filters try to what is okay pool 3 inception for A for B for C for D Shin models PC fully connected layers classic softmax. Why is GoogleNet efficient? One-to-one convolutional reduce computation. Instead of processing 3 to 3 and 5 to 5 directly, it applies one-to-one convolutional to reduce the number of input channel. This reduces computation while keeping useful information. No fully connected layers. Instead of 1000 neuron fully connected layers like in VGG, work uses global average pooling, which reduce parameters significantly. Multi-scale feature extraction. The inception model allowed the network to learn both small and large details simultaneously. Google NetViz other CNN architectures model 2008 layers parameter 60 million 16 layers hard fewer parameters and implementing GoogleNet chaos want to use GoogleNet inception views while TensorFlow. Improve efficient with the both normalization, inception 2 combined inception with optimize 7 GoogleNet introduced inception models for multi-scale feature extraction. It outperformed AlexNet VGG with the fewer parameters. It's replaced fully connected layers with the global average pooling and later improvement inception V2, V3 for refined efficiency. Want to train Google Net, optimize for GPU acceleration, fine tuning of custom image classification. Cool. Inception network. The idea behind the inception network is to realization that the size of object in picture can vary quietly, so that the size of the filter matter. Of course, even with a small filter sizes, we can cover large respective fields. The area is covered by a neuron in later layers in hierarchical network. However, this brings with it the challenge of training deeper network. A major component of this network is to combine filters with the different kernel size. For example, one on 3 environment, 5 and the outcomes of these filters are then connected, concatenated to concatenated. For the next layer, the larger the filter, the more the computer is expensive. It's therefore later version of the inception network vectorize and into 1 times n or and equations. This is computationally much more efficient. Not that pooling is included as parallel stream inception layer that gets connected with the output of their other filters. Another feature of an inception network shown in figure 4111b is to use a layer of C filters to compress the channel. Note that when we talk about an N layer of C filters to compress the channel, when we talk about the N convolutional, we mean the convolutional operation in each channel. And that and convolutional, we mean the convolutional operation in each channel, and that we then add together the result of all channels. Keeping the number of channels small also helps with the computational network. Finally, architecture shown in figure 4 showing another interesting features that of using intermediate output for training purpose. The idea is to help players during training to get feedback so that the learning of such deep network becomes more efficient early during the learning phase, while this last feature has not been as useful are several other tricks in later version of the Inception network that helps to build even deeper version. Kiran includes the version 3 of the Inception network called Inception v3, as well as the version that combines these ideas with the skip connection called Inception network. Since the Inception network takes a different size input, we need to load the picture for the screen as shown below. The Inception 3 network predicts a duck with 10% confidence. is convolutional replacing and multiplying n with 1. Convolutional neural networks. Convolutional neural networks. So, we have so far only discussed object recognition. In many applications, we want to go further and also tell where the objects are in the picture. For example, for self-driving car, we want to know for self okay, what and where. We have also object recognition. In many application, we want to go further. In many application, change you see. Okay. They said here, what is it? Okay, so in many application, we want to go further and also tell where the objects are in the picture. For example, for self-driving car, we want to know where the pedestrians are or where the road is. One way of doing this is to place bounding boxes around the object as shown in figure 4.4. A popular architecture for this is called YOLO. You only look once. The idea is thereby to train network not only on a single labels but also on the location x and y, the size h and w and h of bounding box and its confidence. The network does this by dividing an image into an array of grid cells of size where s was set to s equals 7 in the original example. The network makes p prediction of the 5 numbers mentioned earlier, x, y, w, h, and conf, for each bounding box b equal to. In this original example, so what we need x multiplied by x, p multiplied by 5, and plus c. Output node c is here the number of classes which was c equal 20 in the dataset in the original paper. Hence, the output shape of 7 multiplied by t multiplied by 30. Training this network then requires a loss function with multiple components, weighting the contribution of classification accuracy, location accuracy, and the confidence. There are several other variants of YOLO in the literature, but there are of course also other architectures to estimate bounding boxes. So far, we have talked about object recognition, identifying what is dynamic, but in many real-world applications, we need to go beyond the detail where objects are located. This is called object detection. Why do we need object detection beyond recognition? The need of localization in many applications, just knowing what isn't enough. Self-driving cars need to know where and other vehicles are. Surveillance system need to track where people are moving. Medical imaging need to locate we need a method to both recognize object and find their location in an image. How does YOLO work? You only look once. Is a fast real-time object detection algorithm introduced by Joseph Riedemann in 2015. Unlike older method that process an image multiple times, YOLO process the image in a single forward pass, making it much faster. First of all, let's by Joseph Riedemann.
which is a highly influential algorithm and framework used for
YOLO is state-of-the-art object detection algorithm, and it is so fast that it has become almost a standard way of detecting objects in the field of computer vision. Previously, people were using sliding window object detection.
Hello. So today I'm going to be talking about YOLO, which is a
When I moved to Luxembourg, EIB helped me a lot with
Hello. So today I'm going to be talking about YOLO, which is a highly influential algorithm and framework used for real-time object detection, which means it has a very wide range of applications, including video surveillance, self-driving cars, face detection during the pandemic to measure temperatures and that kind of thing. So it's in short, it's a very popular algorithm that's been used a lot in the past several years. And the goal here is simply to create bounding boxes around the objects in an image, and then also to label these objects according to their class. Now, these sorts of object detection methods have been around for several years, but YOLO and its variants seem to capture a desirable mix between speed and accuracy. Now, the actual definition of mean average precision is a bit more subtle than that, but let's not worry about that for now. So as you can see, out of the models that are capable of what we can call real-time detection owing to their speed, YOLO seems to deliver the best performance, despite still being less accurate than some of the slower models. And the reason YOLO is able to achieve this is that it utilizes powerful deep learning architecture, while at the same time using the input image data in a highly efficient way. So just to compare with some prior developed models, the deformable parts model, or DPM, uses filters that represent whole objects and parts of objects to create a detection confidence map using a sliding window technique. And the idea here is that an object is likely present if all of its parts are present, even if they are configured in unusual ways. Now, region-based CNNs do kind of the same task, but differently. Here you have three separate models: a region proposal model, a CNN that extracts a feature vector, and then a support vector machine for each class. Now, these three models, notably, are typically trained separately. And even though there have been many developments on the RNN approach since 2014, the essential idea of region proposal plus classification still applies. Now, the distinguishing feature of YOLO is that instead of looking at an image multiple times, whether it's to apply the deformable parts filters or to inspect the regions like the RCNN, you only look at the image once. So just to summarize how this scheme works, the first step is to overlay on an input image a grid with S grid cells on each axis. Each grid cell then produces two things. One, it produces a set of bounding boxes centered on a point inside the grid cell with associated confidence scores that an object exists inside each bounding box. And then it also produces a class probability map for each grid cell, which essentially tells what object class is most likely to be in that cell, given that an object in fact exists in the cell at all. And finally, it combines this information to yield the object detections. So that's the abstracted framework, but how does it actually work in practice? Well, for each grid cell, we compute a set of output vectors. The first vector is a vector of class probabilities. The second is a set of bounding box parameters, specifying the x and y position of the center of the bounding box, as well as the square root of the width and the height of the box. And I'll explain why we take the square root a bit later. And then finally, we also have the confidence score denoting the model's confidence that an object in fact exists in the box. Now, instead of having just one bounding box, each grid cell will typically have multiple boxes, and this just allows the cell to detectably have multiple boxes. Having just one bounding box, each grid cell will typically have multiple boxes, and this just allows the cell to detect more than one object. Now in practice, instead of having several vectors, we just combine them into one big vector with length b times 5 plus n, where n is the number of object classes, b is the number of bounding boxes per grid cell. And in the original paper, the authors use a 7 by 7 grid with 2 bounding boxes per cell. And the authors 5 plus n, where n is the number of object classes, with length b times 5 plus n, where n is the number of object classes, b is the number of bounding boxes per grid cell. And in the original paper, the authors use a 7 by 7 grid with 2 bounding boxes per cell and 20 classes. So for each grid cell, we output a length 30 vector. But how exactly does this model just go from an input image to these output vectors? Well, simply, we just use a CNN, a convolutional neural network. Now, this architecture just consists of a stack of convolutional layers that distill an image into a more abstract representation, followed by 2 fully connected layers that transform this into an output vector for each grid cell. And the 3 channels in the input just represent the red, green, and blue channels in the image. Cool. So now that we have an idea of how the model works, let's look at how it is trained. Let's say we are trying to predict, say, this bounding box. Now the center of the bounding box is at this point here, so this grid cell will be responsible for it. Well, let's say we've predicted this green box here, along with the 5 parameters that define it: the XY location, the width, the height, and the confidence. And we want to somehow penalize the prediction because it isn't exactly the same as the parameters that define it: the XY location, the width, the height, and the confidence. And we want to somehow penalize the prediction because it isn't exactly we want to somehow penalize the prediction because it isn't exactly the same as the ground truth. But what would the ground truth values be? Well, for the class probabilities, this is simply 1 for the correct class and 0 for everything else. Note that this assumes that the classes are mutually exclusive. And with later versions of YOLO, I think starting with YOLO version 3, the model is actually capable of multi-label classification, where two classes can exist simultaneously, such as dog and animal. But YOLO v1 just predicts one class. So that's cool. Now let's see how we calculate the coordinates of the ground truth and predicted boxes. Well, x and y are usually calculated with respect to the top left corner of each individual grid cell, and they are also expressed as a proportion of the total grid cell dimensions. Meanwhile, the width and the height are expressed as a proportion of the total image dimensions. Hence, these all fall into the 0 to 1 range. So just to take a quick example, let's say that the coordinates of the point are 16 and 44 pixels respectively from the top left origin of the entire image. Let's say each grid cell is 10 by 10 pixels and the image has 7 grid cells on each axis. Then the x and y values are 0.6 and 0.4 respectively, where the percentage sign here is just the modulo operator. And the width and the height are obtained by dividing by 70. Yeah, well, so what about the confidence? Well, essentially with confidence, the question we're asking is, does an object appear in the grid cell or not? And confidence is the score attached to the positive answer of that question. So let's say that we have these ground truth bounding boxes with these center points and these grid cells responsible. Then, in every grid cell except for those grid cells, the ground truth confidence is set to 0 because there isn't an object there. Meanwhile, in the green grid cells, the ground truth confidence is simply the intersection over union of the predicted and ground truth bounding boxes. Just to review what intersection over union means, the intersection between two sets, or two boxes in this case, is the area of the shared region. So it's the middle figure here, while the union is the combined area of both of the boxes without double counting the overlap. So the intersection of a union of A and B is then simply the intersection divided by the union. So it's essentially a measure of the degree of overlap between two boxes or sets more generally.
Naučím ťa programovať od absolútnych základov v JavaScripte a počúvaj zdarma za 0 peňazí. Tento kurz ja už...
So, the ground truth confidence is simply the IOU of the predicted and ground truth boxes. However, we know that each grid cell can produce multiple predicted boxes. So which one should we choose? Well, during training, in order to calculate the loss, we just use the predicted box that is the highest IOU with the true box. Incidentally, the authors of the original paper note that by assigning only one predicted box to each ground truth box, the different predictors are able to specialize and perform better on certain object classes or aspect ratios or whatever. Now, similarly, during inference, if we have two predictions, P1 and P2, then if the IOU between them is greater than some threshold, we only keep the one that is associated with the higher confidence in the presence of an object. Now, this whole process, called non-max suppression, just trims down the predicted boxes to prevent any overlaps between them. So, now that we know how all of the box parameters are calculated, let's see how they are used in the loss function. Now, the total loss function is basically just a sum of two terms, the object class loss, which operates on the class probabilities, and the localization loss, which operates on the bounding box parameters. And this is what the class loss looks like. So instead of using cross entropy or anything like that, we just take the sum squared error between the predicted and ground truth class probabilities, summed over all classes and all grid cells. Now this interesting symbol here just means that we're only considering the class loss of a grid cell I if an object in fact exists within that grid cell. So recall the probability map that I showed earlier. Here there are plenty of cases where the model has predicted an object class where it's actually a background, and we're actually not counting those cases in the class loss. So class loss only deals with cases where an object has been mistaken for another object, and not where there is in fact a background. So what about the localization loss? Well, this is also split into a confidence loss and a box coordinate loss. The coordinate loss is summed over all grid cells and all bounding boxes in each grid cell, but it is only counted for those cases where cell I contains an object and box J is deemed responsible for that object. So here we sum the squared error of the x and y coordinates as well as the square root of the width and height. We also scale this entire thing according to a parameter, lambda chord, and I'll explain why this happens in a bit. Now, the confidence loss has a very similar form, except that the grid cells which do not contain an object are scaled by a parameter lambda no object, while those that do in fact contain an object are not scaled. And again, I'll explain why this happens in a bit. So here is the entire loss function. What's apparent is that we're just using squared error to obtain good values for the class probabilities and all of the bounding box parameters. So in this sense, object defect detection is just reduced to a regression problem. And this gives YOLO a sense of simplicity. So it really is just regressing all of these values here without anything fancy like, cross entropy losses or anything like that. So from this, we know that YOLO works very well, but what are some of its limitations? And here I'm talking more specifically about the first version of YOLO. Well, first of all, of course, each cell can only contain one class. So or it can only predict one class, should I say. So if, say, one dog and one bicycle appear in the same grid cell, then this presents a problem. Moreover,
So, yeah, there are new change in the plan. I need to restructure them. Like, first of all, I don't know, I just started with these AI things, foundation, fundamentals, and machine learning. I believe this is the main topics for this one. So just put them in a way that I can understand what is AI, what he can do in general, if it's what I need to have focus more. Now I'm just listing these things. What is to learn? Linear algebra. So I think I should finish this one from this week. This machine learning book, this one. Like I put the plan, I really need to master it. I will just now go through it one by one. Like I'm just gonna read it just to have a clue what is going on there. Then I will follow this schedule. The foundation, linear algebra, probability, statistics, Python. I need libraries as well. Structure, algorithms, time 14 weeks, 3 months. I think I can do it. By touch experiment, yes. So, programming skills, machine learning fundamentals, deep learning, advanced AI topic, practical AI skills, cutting edge machine learning. These topics with these have been covered. This one multi-layer perceptron, this one Captron convolutional. Oh my God, logistic regression roadmap. And yes. So, first of all, like these topics related to vector matrix. عيني أنا في عينها والقلوب بعين
Download Stephen H. Friedberg, Arnold J. Insel, Lawrence E. Spence free PDF.
What is linear algebra? At its heart, it's a way to solve systems of linear
Hello. Hi, I'm Jim Heffron. This is a series of
eToro představuje, jak investovat do akcií. Za 30 sekund. Otevřete aplikaci, klikněte na položku objevit, vyberte akci.
Hello. Hi, I'm Jim Heffron. This is a series of videos that are based on my undergraduate linear algebra textbook. The idea here is to enable a person to work through the textbook over the course of what would be sort of a typical semester for an undergraduate first linear algebra course. So I have a couple things that I wanted to say by way of introduction. So let's get started. So this, the book covers, and these videos will cover, a standard linear algebra course, undergraduate linear algebra course. It covers Gauss's method, then vector spaces, then linear maps, homomorphisms, then it goes on to cover determinants, and finally finishes with eigenvalues and eigenvectors. So that would be kind of what a person would typically do over the course of an undergraduate U.S. Semester. Okay, you can use these videos either as part of a standard course, or as a supplement to a standard course, or as something that you can study on your own. A lot of people use the textbook as for self-study because it's freely available. Any of those is great. However, if you're studying on your own and you could use some tips to be more effective, then I can recommend a resource. I'm going to put a link in the description for this video. Of course, you can Google around for yourself, but just in case you're looking for some recommendation, I'm happy to put one in the link. No connection to me, just I found it useful with my students. So the idea of this presentation is that for each topic, let's say chapter 2, section 3, part the first subsection, you can first watch the video. It might be 20 or 25 minutes. Some of the longer subsections I've broken up into 2 videos, a part 1 and a part 2. So you first watch the video, then you study the book. So having watched the video and gotten some idea of what's happening, then you open up the book and go through the examples and the theorems and the proofs in the book. And then you're ready to do the homework. In the homework, I've check marked some of the exercises. I would do at least those. The answers are available. You can download the answers from the same place you download the book from. Again, look in the description of this video. And so you can verify that you've done them right. The answers are completely worked. So if you get stumped on a question, you can, after trying it, you can go and look and see, oh, I see, I should have done. Okay, so the answers are completely worked. So they should be usable to a person who is on their own. Okay. I can also recommend the linear algebra videos by the YouTube author named 3 Blue 1 Brown. Just go to YouTube and search for linear algebra 3 Blue 1 Brown, and you'll find them. They're just wonderful, just delightful videos. However, I have to say, I have to caution you to kind of finger wagging before I leave here, and that whatever resources you use, those videos, for example, these videos here, that you have to watch, you have to do the homework. It's absolutely critical that you do the homework. If, for example, you say to yourself, well, I got a 45-minute bus ride. These videos from Heffron are 25 minutes each, so I'll watch one video a day, and after so much time, I'll have learned linear algebra. No, you won't. You'll have watched a bunch of videos. The way you learn the material is by doing the homework. The video resources, either from me or from 3 Blue 1 Brown or whatever other videos you find online, and there are a lot of good ones, those are great. But until you have done the homework, you have not learned the material. So if you have not done a lot of homework, enough homework so that you start saying to yourself, okay, yeah, I get it already. If you have not done a lot of homework, then you simply have not learned linear algebra. You can't watch videos. That's all there is to it. It's like learning to play a violin. You can't learn to play a violin solely by watching other people play violins. That's just not how it happens. Okay, enough finger wagging. Nice to meet you, and I hope that you enjoy the videos. Hope you find them useful.
Uh, okay, for today I'm gonna stop till here. And today it's February 23rd, 2025. Cool.